Okay, so spontaneity. Like I said, thermodynamics is ultimately about why reactions happen. Spontaneity is just saying whether they happen or not. So, does the reaction happen? If it does, if it happens without us having to force it, then the reaction is spontaneous. If the process doesn't happen, then it's non-spontaneous. Now, just because a process is non-spontaneous doesn't mean that we can't make it happen. You can use energy, like electricity or something, to force it to happen. Or you can change the conditions that the process is present in. If you change temperature or pressure, that might be enough to change it from non-spontaneous to spontaneous. For example, water will spontaneously freeze at negative 10 degrees Celsius. You don't have to do anything. Okay? But at positive 10 degrees Celsius, it is not spontaneous. At positive 10 degrees Celsius, you expect ice to melt, not water to freeze. Conversely, burning wood, well, that's spontaneous at all temperatures. Okay? Wood, once you get it started, will just keep on burning, no problem. I mean, the fact that you have to get it started, that's because of something we call activation energy. There's always a barrier between reactants and products. If there wasn't, you wouldn't have the reactants in the first place. It would just be the products. But spontaneity is about whether the reaction wants to go. Okay? So wood will continue to burn all on its own once you get it started. So, if a reaction is spontaneous as written, then it's spontaneous, A going to B. But if it's non-spontaneous, then we say it's spontaneous in the reverse direction, B turning into A. Okay? And if it's not spontaneous in either direction, that means your reaction is sitting at equilibrium. A is turning into B at the same rate that B is turning into A. Okay? It's not a static situation. The reactants and products are continuously churning, going back and forth. But it's happening at the same rate, so the levels of each stay the same. That's what equilibrium is. That's a big topic in the second semester. Now, enthalpy is not enough, obviously. Endothermic reactions, exothermic processes, these can all be spontaneous. For example, water spontaneously boils at 105 degrees Celsius. Okay, that's an endothermic process. But water also spontaneously freezes at negative 5 degrees Celsius. That's an exothermic process. Both are spontaneous depending on the conditions. So enthalpy just isn't enough to tell us whether or not something is going to be spontaneous. The information that we need is entropy. Now, entropy is a whole nother thing. It is it's a big thing, a difficult thing. So let's go ahead and get started on entropy. What is entropy? This is another hard thing to define, but it brings us to the second law and the third law, eventually, of thermodynamics. The entropy of an isolated system will always increase. Contrast that with the first law. The first law says that the energy of an isolated system is constant, but entropy will always increase. So the entropy of the universe is an isolated constant, or is an isolated system. So the entropy of the universe will always increase, at least for any spontaneous process. Now, mathematically, we define entropy is change in heat over temperature. But you'll notice that we're getting super calculus-y because we have lowercase d s is greater than swoopy d q over t. Entropy is a state function, so it gets the ds. But q, heat, is a path function, so it has to use that swoopy d. Now, if you're having trouble sleeping, there are a lot of different ways to state the second law. So you can go to the Wikipedia page and look at them and just over and over and over, different mathematical formulations, different formulations to explain and analyze and take advantage of the second law of thermodynamics. So what is entropy? Entropy is randomness, disorder, possibility. It's freedom. Okay? So the more freedom a system has, the more possible ways there are of arranging the system, the more the system can do without changing to another state, then it has greater entropy. So, coffee and cream, unmixed, boring. This is low entropy because if they're staying separate, then you can't put, cream on the coffee side and coffee on the cream side. Okay, there's fewer opportunities, less possibility. But on the other hand, in the middle, or at the other end, when they're fully mixed, that is the highest entropy. Entropy is maximized because you can switch any portion of the mixture with any other portion of the mixture, and it will look exactly the same. Okay. You have the greatest amount of possibility, but in the middle, that's when things are interesting because things are happening. It's no longer completely unmixed. It's no longer fully mixed. It is mixing. There's something going on there. So in terms of the universe as a whole, this, at the very beginning, this really, really low entropy state, that was the beginning of the universe, the Big Bang. Then at the very end, and everything is fully mixed, the maximal entropy, well, that's the heat death of the universe. There will be no more possibility of anything happening. Here in the middle is where we live, where energy, where the universe is proceeding from the low entropy state to the high entropy state. Things are flowing downhill. Things are happening. The light that comes into us from the sun is low entropy light, and as it travels downstream through the web of life, it increases over and over and over again in entropy until finally it is released back into the universe as high entropy heat. So the reason life can exist and evolution proceed and all these wonderful things that make history happen, that make history interesting, is because we have this big, bright, hot point in the sky and an otherwise cold, dark sky pouring energy into us that we can take advantage of over and over and over again before we finally release it back out into the cold, dark sky as heat. So, entropy and physical processes. The simplest stuff is, solid, liquid, gas. Solid has the lowest entropy. The particles are locked down. They're locked in place. They can't move. So that is the boring, low entropy state. The particles just aren't free. You go from a solid to a liquid, though, the particles are now free to move around within the liquid form. They're no longer locked in place. They're more free because now they're free to move. But a gas has wildly more entropy than does a liquid, because not only are the gas particles free to move, but they're no longer confined to the volume of the liquid. Remember, a solid has both a definite shape and a definite volume, low entropy. Liquid no longer has the definite shape, so it's more free, but it still has a definite volume. The particles are still confined within that volume. But the gas is completely free to explore any space that it exists within, so it has wildly high entropy. So you go from a solid to a liquid to a gas, you have increasing entropy. You go from a gas to a liquid to a solid, you have decreasing entropy. Now, there might be isolated substances that violate that for going between solid and liquid, but overwhelmingly, for most every substance out there, you're going to find that the solid has lower entropy than the liquid. So, how about chemical processes? Now, that's obviously going to be more complicated because different substances have different values for entropy just because they have different physical arrangements within the molecules and inside whatever substance, the expanse of the substance. But, rule of thumb, look for gas. More gas typically means higher entropy. So, for example, when you have hydrogen and oxygen combining to make water, you have 2 molecules of hydrogen and 1 molecule of oxygen makes 2 molecules of water. So you're going from 3 moles of gas to 2 moles of gas. That's a decrease, so you're going to see a negative change in entropy. Then we have methane and oxygen. 1 molecule of methane combines with 2 molecules of oxygen to make 1 of CO2 and 2 of H2O. So you're going from 3 molecules to 3 molecules, all of it gas, so not really zero entropy change, but you can say that it's going to be a very, very small entropy change in whatever direction it is. And coming down here for the decomposition of calcium carbonate, you go from a solid to a solid and a gas. So from 0 to 1, you're going to see a positive entropy change. Now, in reality, yeah, it's more complicated, and uses math. You can measure the change in enthalpy for a reaction. So for water, it is 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water, and the change in enthalpy for that reaction is negative 88.8 joules per Kelvin. Yeah, joules per Kelvin. Entropy is weird. The reaction will always take place at some temperature, and eventually we will combine entropy and temperature so that we can use it alongside enthalpy. But in the meantime, we can do entropy stuff by itself. Okay. And we do that pretty much exactly like we do with enthalpy. Here we have a chart, same as, well, very similar to the one we saw before, where you have a change in enthalpy, or the enthalpy of formation, and then you have, we'll ignore G for the moment, we'll get to that in a minute, and then we have entropy. These numbers are a little bit weird because it's kilojoules per kilomole instead of kilojoules per mole, but that's just a thing. But first thing, big thing I want you to notice, enthalpy of formation for a substance, for a pure element, is always going to be 0. But that's not true for entropy. Entropy is a measure of the different ways you can store energy in a substance. The degrees of freedom. And everything's always going to be moving. Everything's always going to be at least a little bit free. So there is no, for the most part, 0 entropy. The third law, in fact, says that you can only have 0 entropy for a perfectly ordered, an absolutely non-at-all random crystal of hydrogen chloride at 0 Kelvin, at absolute 0. Okay? So the only time you could have 0 entropy is if you had something that was absolutely perfect with absolutely no thermal energy. So everything else is going to have a non-zero entropy. But the enthalpy of formation would still be 0. Okay? So enthalpy and entropy are very different things. So let's work through this example. We are combining cyclohexane, or actually no, that's benzene, excuse me, with oxygen to produce CO2 and H2O. And this looks exactly like the Hess's law type of problem, because it's just products minus reactants. You take the entropy, you multiply it by the number of moles that you find in the table, and then products minus reactants. So we have our balanced chemical reaction. Let's go ahead and bring up this guy. So, okay. Accidentally bumped my microphone. Just wanted to make sure I hadn't screwed anything up. Okay, so 2 benzenes plus 15 oxygens yields 12 CO2 and 6 water. So it's liquid benzene, gaseous oxygen, gaseous carbon dioxide, and liquid water. So we come over to the table, and we start looking things up. Wow, that kind of works perfectly. It's almost like I planned it. All right, benzene. Benzene is right there. 269.20. Another thing you'll notice is that the entropy is always positive. It will, the entropy of the substance will always be positive. The delta S for a reaction might not be. Let's see, this is kilojoules per kilomole. Kelvin. So let's see. Okay, so that means joules per mole Kelvin. Oh no, so joules per mole Kelvin. There we go. Oh, okay. Well, so there's two of these. Okay, so I'm sorry, I'm having to sort of translate their units into the units I'm more accustomed to working with. All right, now oxygen. Oxygen is up top. It's 205.04. And there's 15 of those. So, first thing, something that you can note here is that the oxygen is actually slightly less free than the benzene. That's kind of strange because benzene's a liquid and oxygen's a gas. But it has to do with the fact that benzene, even as a liquid, has ways of interacting among the molecules. So you can get weird things like that. And while we wait for my calculator to finish loading, really quick, we're going from 15 moles of gas to 12 moles of gas. We should, kind of rule of thumb, expect a negative change in entropy for this reaction. So 205.04 times 15. Oh, 75.6 joules per Kelvin mole. All right. Now we need our chart back up. Come on, computer. There. So for CO2, carbon dioxide, it's right there. 213.80 times 12. Okay, Wesley? You just miss your putty? Stop playing with you. 2565.6. And liquid water. So compare, there's water and there's water vapor. Water vapor is pretty typical, higher than liquid water. So liquid water is 69.92, and there are 6 of those. Or 19.5 joules per mole Kelvin. All right, so now we're going to add our products together. $985.1, and we're going to add our reactants together. $3614.0, and now it's products minus reactants. So 2985.1 minus 3614. So the entropy change for this reaction is negative 628.9 joules per Kelvin mole. All right. So yeah, that is what we expected. There is a negative change in entropy for this reaction. It's a bigger negative change in entropy than we would have expected just because of this guy. All right, so let's go ahead and close that up and continue. So now here's another example. Go ahead, pause the video, and see if you can't work through this one yourself. This is methanol with oxygen making CO2 and H2O. All right, welcome back. Let's power through this. Okay, so methanol, methyl alcohol, liquid, 126.80. Oxygen as a gas is 205.04. CO2 is a gas, 213.80. Water is a gas, 188.83. Thank you. Hey, go get out of here, Wesley. All right, so CO2, 2 times 213.80 plus 2 times 188.83 minus 2 times 126.80 plus 3 times 205.04 equals negative 63.46 joules per Kelvin mole. All right, and that's about what we expected, a negative change in entropy because we're going from 3 moles of gas to 4 moles. Wait, no, that's not what we would expect. We're going from 3 to 4, so we would expect it to go down, or we would expect it to go up, but instead it went down. And again, that's because you can get some unexpected results. Methanol, even as a liquid, has a surprisingly high degree of entropy. Methyl alcohol, liquid, 126.80. Where the heck did I get that number from? Oh, no, that's the one I used. But I wrote down 213.80 for some reason. I wonder what the heck. Oh, I see. I was using that's CO2 and that's water. And that's methanol and that's oxygen. No, I got it right. But still, methanol does still have a fairly high entropy. I mean, it's not as high as any of the other three, but still surprisingly high. So we have a negative change in entropy just because of that, but also oxygen is relatively high. Okay, so in any event, let's continue. Okay. So that is that. Okay, we can calculate entropy in the exact same way we calculate the change in enthalpy for a reaction if we're using enthalpies of formation. Nothing particularly new here. The difficult part is understanding what the heck entropy is. Just trying to remember, entropy is sort of like freedom. The more free the substance is, the more ways you can arrange the system that are, without actually having to do any substantive change to the system. Those are measures of entropy. I know it's difficult. This is a fairly abstract thing. But rest assured that on the test, you're mostly going to be working with entropy and not explaining entropy. So with that, I'll call an end to this set of slides. I'll see if I can get my dog to calm down a little bit, or at least play with my cat outside of my room. And I'll see you in maybe 15, 20 minutes. I've got dinner to eat. See you in the ground.